Vx plus say V naught, which is a constant, and then E plus V naught. You can add a constant to both sides of the equation, and the problem remains unchanged because potential is a relative quantity. You learn in your ECE 329 that potential is a relative quantity. So you can always change Schrodinger equation by a constant. And so what happens here is that this new E prime will give you h bar omega prime. So the frequency, the Schrodinger, the quantum frequency that you work with is also arbitrary. There's no meaning by itself. It only has meaning when you compare with another frequency. Okay? So this thing will translate to e to the minus I omega prime t. But it's not this time dependence is important. It's a relative time dependence is important. And it's something that you have to be aware of in quantum mechanics. So it doesn't matter where we define the zero potential is in this equation. We can just define it anywhere that we like, and it should be okay. Okay? So we can define Vx to be 0 inside the wall, and then try to solve this problem. We can solve a very simple problem where the potential at the wall goes to infinity, and that it is equal to 0, 0 value on the, it has 0 value. Okay, this is V of x. There's 0 value inside the wall, but infinite values on the wall. This is like a parallel plate waveguide. Like a parallel plate waveguide, except that there will be some difference. Okay? So there cannot be any wave function outside. So phi of x is equal to 0 outside. Phi of x is also equal to 0 outside because this infinite potential one allows for no possible solution. If V tends to infinity outside the wall, and in order for this equation to give you any finite value, okay, the potential function, the wave function has to be 0 outside the wall. Okay? Otherwise, you have infinity times 0 and it becomes undefined. I mean, you can reach some finite value by infinity times 0. So the wave function has to be 0 outside the wall. That's one way to argue it. Another way you can argue it is that you can solve this problem first. You can solve this problem, and this is like a dielectric waveguide problem. You find that in mesh boundary condition, you might get a trap mode inside this wall. And then outside the wall, you have evanescence wave, just like a dielectric waveguide. And then as you raise the potential of this on the outside wall, you'll find that this will become smaller and smaller from the closed form solution. But we would not do that. Okay? I would just argue that the potential outside being infinite gives rise to 0 wave functions on the outside. So you can write down the solution for this case as being equal to sine kx plus b cosine kx. Okay? Sine kx plus b cosine kx. And then let me shift this coordinate system so that I work with this problem in this manner. Okay, so the potential, well, over here actually, so that the origin corresponds to one of the walls. I have this thing. Okay, and that I will have to take sine x as the solution. I will have to take sine x as a solution because the potential has to go to 0 outside, so the solution must look something like this. That is one way we can convince ourselves, and you can go through the mathematics of it as well, that the wave function actually has to have 0 values at the two ends. Alternatively, you can solve this problem first. You can solve this problem and then let the potential outside being going to infinity. You can see that the limiting solution would be something that looks like this. Okay? There's another way to argue it. And another way you can argue it is that if I have this as my equation, if I have this as my equation, I can just look at this equation, and if Vx looks something like this, if this is my Vx as a function of x, and this is my Vx, okay? And that my wave function has to be a continuous function that looks like that, so that there's no singularity produced by this wave function as I take the second derivative. The wave function cannot look like that. It cannot look like that because if I take its first derivative, I'll get a delta function. Okay? If I get the second derivative, I'll get a doublet. And this will produce a very singular term that cannot be balanced by anything else. And there should be a side of x. There's nothing else that can balance this, and because there are no infinities everywhere else. Okay? So this thing must not have infinity. So the worst that it can look is that its first derivative okay, so even the first and the second derivative has to be continuous. That means that if it were to look like that at the boundary, say, if I take its first derivative, it will be positive, and then the smaller positive value. This is psi of x. This is d dx of psi of x. And if I have d squared dx squared of psi of x, I would get something that has a Taylor function here. And then maybe something like that. So the function cannot even look like that. It must be smoother than this. That its first derivative has to be continuous. So the function as well as its first derivative has to be continuous at this point. If you just eyeball this equation. If it looks like that, it's continuous, but its derivative is not continuous, then it will look like that. If you take one more derivative, it produces a delta function. And there are no singularities to match this equation anywhere else. So this function must be smooth to the extent that itself and its first derivative is continuous. Okay, so if you solve this problem, then you find that the function plus its derivative must be continuous here. And if you raise this potential out, okay, the only way that the function and its derivative can be continuous is that it goes to 0 in this manner. And then it becomes like that, as this potential goes to infinity. So I have to take sine kx as my solution, not the other one. The other one would look like that. Maybe it might look like that, okay? And then it goes to 0 like that. It's not possible. So I have to rule out this part. Okay? Is there any questions regarding this? So if you now plug in the let's work with this equation and not with this scale equation or race equation. Then you plug that equation in inside the while v equal to 0, then h squared 2m times d squared dx squared psi of x. This is just a sine of kx now. Okay, must be equal to h squared k squared over 2m psi of x. okay, inside the while. And then this must be equal to E of psi of x inside the while. Inside the while, this is 0, and this must be E of psi of x. And then the energy of the particle now is proportional to that. But we have to pick our k appropriately so as to satisfy the boundary condition here as well as here. Okay, k cannot take on any value. So it has to be that k takes on value only in such a manner that sine of k, let me see what notation I use, ka, okay. Sine of ka must be also 0, where a is the width of the while. Okay, so this gives me ka is n pi. N goes from 1, 2, 3, and so on. Okay, ka must be equal to n pi. So ka takes on discrete values. Because ka takes on discrete values, my energy also follows the value of k in that manner. Okay, n pi squared over 2na squared. Okay. So you can find that the fundamental mode, the lowest order mode, look something like this. Which is a sine wave function. The second one will look something like this. The third one will look something like that. And you can associate the E value with each of them. So the lowest one, E1, is equal to h squared pi squared over 2ma. The second one, h squared 2 pi squared is equal to 2ma squared. And then the third one, I can call this E1, E2, E3 for instance. This one will be h squared over 2ma squared 3 pi squared. Okay. So all these different modes will have different energy. And that energy is actually the kinetic energy of the particle as it bounces back and forth between these two walls. The larger the eigenvalue, the more kinetic energy this particle has, which also means that it has a shorter wavelength. So the thing is that you learn something about k in this course now. K is not just a wave number. K can be related to the momentum of the particle, and hence also to its kinetic energy. And then we have to do something else. We say that sine of x is a, sine of kx is a, sine of n pi x over a, where n goes from 1, 2, 3, and so on, very much like the solution of a parallel plate waveguide, and n should never be 0, and we need to normalize this function. We can normalize this function so that when we integrate with respect to the wave function within the box, this should be equal to 1. Okay? And you can actually work this out. And that you can show that psi of x then is equal to, after normalization, 2a sine n pi x over a. Okay? And you can also show orthogonality. That it should be psi nx, okay, psi nx, psi n conjugate x, dx 0 to a is equal to delta nm, delta nm. And this is very much like what you have learned in matrix algebra. You can think of this in a matrix operator. Okay, you can think of that as being a matrix operator. That matrix operator operating on the eigenfunction gives you an eigenvalue times that eigenfunction. You can show that if I have a second eigenfunction, and this maps to a matrix problem like this, A dot psi of n is equal to, let me call it En psi of n. And think of this as being the matrix times the vector. This is a matrix times a vector, and this is another matrix times another vector. Okay? And we prove orthogonality of such a kind of matrix operator. We show that size of m conjugate transpose dot A dot size of n is equal to something, and finally we were able to prove this fact that this is true. Delta mn with a Cn. Okay, remember you did some proof like that for this set of equations. Yes?
This is the psi of m in the integral. Psi m conjugate.
Yeah, thank you for pointing that out. Sin n, this is sin n. Okay? So we prove something like this, that if we have two eigenvectors of an operator A, and this is A summation, then we can show that the eigenvectors are orthogonal in this manner. Okay? And this is exactly the manifestation of that orthogonality property in Hilbert space. We can prove this property later on. If you expand this concept to Hilbert space, you get this kind of orthogonality relationship. Okay. I guess we'll take a break here. Take a 5 minutes break. Are there any questions before we take a break? Yes?
I'm just curious about this one because you just mentioned the first derivative of the wave function must be continuous.
Right.
It seems to me that this infinite potential about the first derivative of wave function is not really continuous at two endpoints.
You're right. That's a very good question. That is something that bothers some people. Seems that the function is zero on the outside, okay? But this picture is actually the limiting case of this other problem. That is, if I were to solve this problem, it's a limiting case of a finite potential wave problem. Okay? If I were to look at this solution, it will look something like this. It will have to satisfy the mathematical property that I have convinced you of just by eyeballing this equation. So if I were to sketch the wave function, it will have to look something like this. The wave function and its derivative must be continuous. So it must look something like this outside. Okay? So as I make the value of this potential going up to make it into an infinite potential wave, this thing will start to look more like this now. Gets very, very small outside. Okay, but it also decays rapidly to zero outside. So you can think of a wave function out here that is joined to this wave function but decaying rapidly outside to zero. Okay? It decays rapidly outside because this exponential decay will become more and more rapid as you raise this potential wave. So it goes to zero rapidly. So you almost don't see it, but there actually is a wave function here creeping in and rapidly rising to this one that matches up with this one. So both the function and its derivative are actually continuous there. If you think of it as a limiting case of this, the function and its derivative are continuous there. That's a limiting case of it. If we just look at this, it seems to have violated that. Okay? So any other questions? That's a good one. Let's take a 5 minutes break and come back. Okay?